So this is our second lecture in vapor power cycles. We spent a lot of time talking about the Carnot vapor power cycle. When you were first introduced to something like the Carnot vapor power cycle, you started with just an empty box, and you started with heat transfer into the system from a high temperature coming into the system across a boundary at high temperature. So QH coming in at TH. And your goal was to convert as much of that into useful work as possible out of that system. And then you had to reject some QL at a lower temperature TL. We developed, way back at Thermo 1, the thermal efficiency of this cycle. And that was one of the great contributions of Carnot. That's why we still kick around his name and use it in thermodynamics. 1 minus TL over TH. What does that tell us? If you want high thermal efficiency, what should you do to TL? Make it as low as possible. If you want a high thermal efficiency for a heat engine, this is a generic schematic of a heat engine, you would want TH to be as high as possible. That applies into the Rankine power cycle. That same logic. We want to bring in all of our heat at high temperature into the working fluid, into the steam generator, boiler, etc. We want to reject in the condenser, wherever we're rejecting it, as low a possible temperature as possible. In the Carnot, it's all brought in at TH and all rejected at TL, but when we get to real operating power cycles, it's not all brought in at TH. Some is brought in at lower temperatures, some at higher temperatures. But the goal would be shifting it and get as much brought in at high temperature. What we really do is we look inside the black box of the heat engine and we say, you know what? That's a boiler. And that heats up water and converts it into steam, and then we go to a turbine which is connected to a shaft. And then we go to a condenser which rejects heat, and then we go to a pump or compressor, call it a pump. And so we could look inside and say, oh, this is actually how it could operate with a system with 4 components and the fluid flowing in a continuous cycle through those 4 components. Well, then we went to the Rankine power cycle, and we'll talk more about efficiencies or how to improve. But I think if you really understand the Carnot, you're well on your way to understanding why things are done the way they are done in actual power plants. Again, the biggest idea already is given. We already covered it. It's a TL as low as possible. You can't really do much about that. Sometimes you just have to, that's the lake water you reject it to. TH as high as possible. You try to get your metals so that they can handle the high temperatures so that your fuels can actually burn easily at higher temperatures than what it's used at. But metallurgical considerations often limit TH. Okay. So all Q in at TH. That was true for the Carnot, not true for the Rankine. High temperature is good, true for both. All the QL out at TL, that's going to be true for both Carnot and Rankine. Pretty much the condenser is the lowest temperature, and that's where we're rejecting heat out of the cycle. And TL is good, that's true for both. So the big difference is the Rankine versus the Carnot, not all of the, do I repeat myself? Is that annoying? No. Sometimes I think my kids are like, I heard it, Dad. Quiet. You know, don't tell me again. But I think maybe from the university, I just say things because I know that the first time I hear something, it doesn't catch. It doesn't sit. So anyway, I usually repeat myself too many times. So when we looked here, that was the big difference between the Carnot and the Rankine cycle. We noticed that, hey, we had a lowering in the thermal efficiency, and we really wanted to explain why. And it wasn't because of problems in the turbine. The turbine was great. It wasn't because of problems in the condenser. The condenser was great. It wasn't because of problems in the pump. The pump was great. It was right in here. And it really is a lot of insight as to why the boiler. And it's because in the Rankine cycle, this fluid coming into the boiler is cold. And it has to be heated up before it can boil to then go out as saturated vapor. Okay. So one of the things I did that I didn't do last time, but since then, I went and I took that same problem, the same problem of 8 megapascal boiler pressure and 20 kilopascal condenser pressure. It introduced a fifth state, which is not needed in analysis, but it helps add insight with this fifth state. And what is the fifth state? The fifth state is at 8 megapascal, it's not saturated vapor. That's what you're going to come out of the boiler at, saturated vapor. But somewhere in the middle, it finally gets to become saturated vapor. So between state 4, kind of the inlet to the boiler, state 4, it's 60 degrees coming in. It has to be warmed up for this problem up to 295 before it starts changing phase. And once it starts boiling, it stays at 295 till all the liquid becomes 100% vapor. And that's what goes out at state 1. So then the question is how much of the heat into the boiler, what fraction went to just getting it warm, getting the liquid warm? And then what fraction of the heat in the boiler actually went to boiling it, making vapor? Because the vapor is what's needed to get across to push the turbine blades. All right, well, it's a whopping 42%. How did you make that calculation? First of all, it's a startling large fraction of the heat, isn't it? I would have hardly guessed that, right? Just getting it warm, the liquid warm, before it starts changing phase. Well, because we introduced state 5, the heating from 4 to 5 is really a difference in the enthalpy. And so the key parameter is look how much the enthalpy had to go up between 4 and 5. That difference is the heat brought in, that phase, or that between those two states, section 4 and 5. And so 1,057 kilojoules of heat transfer in per kilogram of fluid. And then the rest from 5 to 1, you just take the enthalpy of saturated vapor minus the enthalpy of saturated liquid. So H1 minus H5, that gives us 1441.4. Hey, what's another name for this? Isn't that just HFG? Yeah, the heat of vaporization. Yeah, that's just HFG. You can go and look in your tables. Do you want to pause and do that? I blew through this lecture too early at the 8:30. The people were like, "You're done?" Yeah, because I didn't ask them to do anything. Would you like me to ask you to do something? Do you have your tables? Can you verify that that's HFG? There are some other things we could verify in this table, but later I'm going to ask you to do some more calculations, so keep your tables handy. So yes, you verified that number. Okay, so what I did was I said I'm going to sum the components for the two heats, and then this is the total. I've just summed it right here. And then, that's 42% of that, and that's 58% of that, and that's how I got the fractions. Okay. So what we want to do is we would, one of the schemes, we won't get to it today, it's called regeneration. I didn't pick these terms, but it's basically with feed water heaters to bring it in warmer. Okay, notice we get the decent, very low backwork ratio, which is great. And we still have pretty high thermal efficiency. Let's press forward now. So the idea, if you want to have more heat brought in at high temperatures and you have that phase change happening, well, try to get that TH, which is basically Tsat, as a function of pressure, boost the boiler pressure, the pressure of the boiler. If the boiler pressure goes up, then at temperature at which it's changing phase goes up, TH is up, better for performance. People knew this at the beginning of steam engines. So what would they do? Crank up the boiler pressure. And then what would happen? Which resulted in great loss of life. The explosions every now and then. And why is the society, American Society of Mechanical Engineers, what is its roots? When was it started? Why did the engineers get together and say, we need to do something about the carnage that's happening out there in our cities, in our boilers? They said, we're going to come together and have a consensus on how to make good boilers. And you have to make boilers with our procedure, following, basically, they had the boiler pressure vessel code. If the code, you comply with the code, you can get a stamp, and the ASME stamp put on your boiler pressure vessel. When somebody wants to buy it, they may look at your code and say quality, safety, and they may select that. All voluntary, and then all of a sudden then the states adopt it as code. Like you can't purchase and install a boiler pressure vessel that's not meeting those standards. So it starts voluntary by engineers coming together to save lives, and then progresses. And now it's just like, it would be ridiculous. I mean, you wouldn't want to buy anything that's so could have such large bad consequences that you would want to make sure it's a safe piece of device. Anyway, let's press forward. Okay, condenser pressure. Basically, in the winter, your lake water is a little cooler than in the summer. And so it's kind of dictated by where you're cooling it. Or if your power plant's located in Alaska year-round, it's cooler than year-round in Corpus or San Antonio or Houston. And so your high temperature could be the same, but the low temperature could be different because you're able to get cooler lake water to reject it to. Or even they reject it to not just lake water, river water, ocean water, atmospheric air. There's a number of schemes, depending what you have available. If you have a nice river flowing by, just dump the thermal energy in the big river. But around here in Texas, we build lakes for cooling purposes on our power plants. Okay. The other one is, once you have that idea down, well, don't just stop pumping in heat when the fluid becomes saturated vapor. If you just keep at that high pressure pumping in heat, the temperature at which it's coming in is higher. You superheat it. Yeah. So it comes out superheated vapor. That's actually a lot better to go into the turbine than just saturated vapor. Reheat. Okay. Well, when we take a look at our TS diagram, if you expand it without superheat, there's pretty low quality steam. Maybe that quality, what was that quality over here? That quality was around 70%. That's way too low. What does the quality mean? This is a Thermo 1 review. Anyway, I got digressed. Let's press forward on this problem. So once you have the idea of reheat or superheat, the idea of reheat. So what you do is expand to a certain intermediate pressure, reheat it, and then expand again. And then regeneration we're not going to get to today, but that's attacking the coldness of the water going into the boiler. So I encourage you to get a decent temperature entropy plot and go ahead and show what it looks like if you actually increased the boiler pressure. Let's say this is an 8 megapascal line and you went up to a 14 megapascal line. You would get a higher temperature at which a lot of the heat was brought into the cycle. Good for performance. Take a look at what happens when you change the condenser pressure. Maybe it dropped to from 20 to 10 kilopascal. You're going to drop that temperature. Again, that's typically controlled by the lake, cooling water lake temperature. Superheat. I don't think we've done this one. Let's say we're at 8 megapascal. It's saturated vapor, but somebody says, no, that's only 300-ish degrees. I think, what was it, 295? Let's put it back and get it to continue to be heated in our steam generator or boiler and come out maybe at 440 degrees. So if it comes out at 440 and 8 megapascal, it's superheated. When we expand it, if we expand it all the way down, you can see that the quality has improved. It's higher quality. It's not going to be a practical issue of having a low quality steam at the exit of our turbine, which is poor for performance. Did I mention why? As a practical issue, the steam exiting your turbine needs to be fairly high quality. Okay, it didn't. So what again is the quality? It's a mass fraction. So if it's high, it's all vapor. If it's lower, I'm getting liquid. Now, how does water as a two-phase mixture go out of a steam turbine at a high rate of speed? Well, it's going to come out like a fog. And what happens is the little water molecules coalesce and they bind up and they become little droplets. A thicker fog, bigger droplets. And so when it's flowing out, those little droplets, think about the mass density in that little droplet compared to the mass density in the vapor that's around it. Well, they're very dense. So if there's any bending, turning of the fluid, which there are next to veins when it's in your fluid mechanics, we do all this vein calculations, pushing, getting a pressure and a torque on a force on your veins. So your fluid stream comes in and turns, and then you get this force in that direction and helps rotate the machinery. So anyway, the gas, vapor, the dense stuff, oh sure, it bends and turns. What about the solid little chunk of high density water that's in it? It wants to still go on a straight line, and so it's going to possibly go and impinge on some of your blades. Now you have something like a water droplet, pretty incompressible, pretty hard, impinging on metal. That's not good for the metal. And they'll get a little pressure pulse, and it's actually sometimes the popping back of the pressure wave that then spall off and eat away or erode, like cavitation. Who's taken fluid mechanics? Cavitation, right? So instead of having gas pockets that then quickly collapse, here you have water that impacts the solid and then does essentially the same type of damage. So high quality steam, we need it out in this vicinity if we're going to exit. So what we'll do is not just superheat, that helps, but we're going to stop and expand it to 2 stages of turbines. So this is an illustration of superheating. Workout problem on superheating. I'm going to skip it and get to reheat. So what we have is we have a high pressure. We still have our condenser low pressure. We have an intermediate pressure. All right, so what about this intermediate pressure? What you do is you expand down to intermediate pressure, then send it back for reheat to the steam generator. And now once you're back to reheat, you could get it back up into the superheated region, high temperature. A lot of heat is added at high temperature, good for performance. And then you expand back again, and the quality at the exit of my second turbine or the low pressure turbine is good, and the quality at the exit of the first turbine or the high pressure turbine is also good. Now you're getting closer to what actually happens in power plants. You're not going to have one turbine doing this huge expansion. You're going to have 2 turbines, high pressure and low pressure turbine at the minimum. Usually they don't have more than 3 sets of pressures. You may have 2 high pressures and 2 low pressures. So you had 4 turbines, but anyway. So this you can see the benefits of. So let's solve this problem. We sketched it on a TS diagram. Here's a word problem. So it would read something like this. Water is a working fluid in a Rankine vapor power cycle. The ideal, meaning the turbine's isentropic efficiency is 100%, and the pump's reversible and adiabatic. So its isotropic efficiency is 100%. We have superheated water enters the first turbine stage, so it's been at that 8 megapascal and 440 superheated up to there. It exits at the intermediate pressure of 1 megapascal. Then it's reheated to 440, then it enters the second turbine, which is down, exits the second turbine at the condenser pressure of 20 kilopascal. And then it's going to enter the pump, leaving the condenser as saturated liquid at 20 kilopascal and go on. So when you're new to a problem like this, a word problem, what is my recommendation? Get a schematic. all your components and make sure that you don't forget to have 2 turbine stages and going back for the reheat. Then, once you have a schematic, illustration, label the states, the unique states, then get a property diagram. So schematic, states, property diagram, a temperature entropy property diagram, and then actually put them on the diagram. Now you're way ahead of the game. If you could do those things, you got this pretty well licked. Because you just get a table of the properties. And I've shown you a couple tables. State 1, State 2, State 3, State 4. List the states this way. 1, 2, 3, 4. Pressure, temperature, maybe quality, enthalpy for sure, entropy. You could put specific volume, but not necessarily. Those are the key ones right there. And then make a table, because you can now work through the system. Oh, I know the pressure here, I know the pressure here. Oh, it's saturated liquid. Oh, it's superheated vapor. I know the temperature. I can get the enthalpy here. I can get the entropy there. You can actually work this whole thing out. You have to be able to. All right, then get a table of the transfers, the energy transfers in each of the components. What are the components? It's the boiler. It's the turbine number 1. It's turbine number 2, the reheater, blah, blah, blah. And there's a bunch of either Q's or W's. Put it all per unit mass. Once you have those, then you go ahead and compute the metrics of interest, like the thermal efficiency back-work ratio. So the work developed by the turbine and the pump, that's filling in this table, as well as the heat transfer in the boiler and the condenser. So, for this problem, I've given you the schematic. I've added extra states 7 and 8 to help us analyze this problem. And so what I'd like to do in the time remaining is to start uncovering parts of the table. And let's see how you can do with the pressures. That's usually the easiest column, because basically it's all given to us. You just have to understand what is the pressure at each state. So I'm going to walk around and you fill it in. Or maybe I should have done this. Maybe I should have asked for a button. All right. Well, how about this? Do those look reasonable? Sometimes it's good to just put in the givens. Where does this piece of information fit into the table? Isn't that the temperature of state 1? So that goes right there, 440. Okay. How about it's reheated to 440? Does that mean the temperature at 2 is 440, temperature at 3 is 440, the temperature is 440? Which one? 3. That's exactly right. So trying to put that information in, you have it reheated to 440. So T3 is given. Let's continue to read. It's saturated liquid at 20 kilopascal. Okay. If I just focused on the temperatures, if I am given that it's saturated liquid and 20 kilopascal, how can I find this temperature right here? Tsat at 20 kilopascal. And we've done that a few times. It's around 60 degrees, right? Okay. Now, you can work on more temperatures, but the key are going to be the enthalpies, etc. If we look at what fixes state 1, those 2 pieces of information fix it, I can get the enthalpy and the entropy at state 1. Right? So, those come out of our table, superheated table. And then, once I know that it's the best turbine, it's going to be no entropy generation, adiabatic, so the exit entropy, do a second law analysis, is equal to the inlet entropy. True? Then, guess what S2 is? Now I've got S2 figured out. I've got P2 figured out. Pressure and entropy fix the state. So let me pause and see how many people can give me H at state 2, knowing that pressure and entropy at state 2. You had a question? So what is the people are working with me on this. What is S of G at that 1 megapascal? That was 6 point, what was it? 5863. And so now you look at this S, compare it to SG at that pressure. It's two-phase. And now you calculate the quality at state 2. That's going to be the S minus SF divided by SG minus SF. Old memories come back, and you find the quality is almost 100%, but it's 98.5%. Knowing that quality, I can now get the enthalpy. How do I get the enthalpy, Professor? That's H of F plus the quality at state 2 times H of FG. And that enthalpy comes in 2747.6. Let you pause. I'm going to pause, and what I want you to do is, as I walk around, a few of you tell me how you're going to get this H and that S for state 3. Because some people are a little ahead of others, some people are a little behind, but this is the best way I can try to engage you, okay? So this was just in a table, the superheated vapor table in the pressure block, 1 MPa, look up at that line of 440 temperature, get the 2 H and S right off the table. Okay, now, this one, how about state 4? How am I going to find S4 right here? Let me pause and walk around. This is an opportunity for some to get this one a little faster than the other ones. Yeah, so a lot of us said, oh, hey, we did this before. We have analyzed the flow through the first turbine. What's the difference between the flow through the second turbine and the first turbine? Both of them are the best turbines money can buy. They're isentropic expansion. So S4 is equal to S3, just like S2 is equal to S1. So boom. And then they say, I've done this before. Let's compare this S with S of G. Maybe I should change color. Compare it with S of G, not at 1 megapascal, but S of G at 20 kilopascal to see if I got into the two-phase region or if I'm still slightly superheated at state 4. And when you make that comparison, what do we find? We went inside the dome where we have a two-phase mixture, and then you could calculate that quality. The quality is like 95.5%. Once you have the quality, get the enthalpy. You kind of work to get this enthalpy column because that's what drives all the Q's and the W's. All right, so you got that state. All right, now state 5, we know the pressure. How would I get, how about somebody who's shy and hasn't answered much today? How are you going to get H of 5? H of F is the saturated liquid's enthalpy at the pressure of 20 kilopascal at state 5. So that's pretty easy. It's H of F. And if you can look in the table, you could probably find 251.4 or a number very close to it. H of F at 20 kilopascal. What table would you look in? Would that be in table A4? A3? Okay. A3, table A3 has it. Okay. Now you can look up that entropy at that point too, but when we go from 5 to 6, we really don't want to interpolate in the compressed liquid table for state 6 properties. We just want to use the approximation that this best pump has a minimum work. That minimum work into the pump is the V delta P. VDP. I encourage you to look at that last time at the end of chapter 6. When you have a specific volume, pressure change, and it's isentropic, it boils down to very simple VDP. This is the specific volume of saturated liquid at state 5. That's what's coming into the pump. And then this pressure change is the high pressure on the outlet, P6 minus P5. I like to work in units of kilopascal. When you do kilopascal times meter cube per kilogram, it's precisely 1 kilojoule per kilogram. Units kind of work itself out easily right there. So I am able to calculate the work of the pump. So usually what I do is I calculate the work of the pump, put it in this table over here. It's about 8.1 kilojoules per kilogram. Now I know that I put a negative sign on that, so I should probably turn this arrow around, right? And in the equation, there's actually a negative sign in chapter 6. So everything works out with the correct sign. And what we have is it is going to increase the enthalpy by 8.1 kilojoules per kilogram.
The VG, did you use the VG for?
No, V5 is V sub F at the 20 kilopascal, the saturated liquid. So that value is like 0.001019 or something. We looked that up earlier, didn't we? Yeah. Okay. So that then, once I have the work of the pump, then the enthalpy at state 6 is equal to the enthalpy at state 5. And because this is a negative, I have to put a negative on the work of the pump so that really you're increasing the enthalpy. H6 is higher than H5. Make sure that you get the signs right? So it's going to come out. What's the difference between these two? 8.1. 8.1. Okay. You can go to that table, compressed liquid table, and you can do that double interpolation, but it will not be as accurate as this one. This is actually more accurate. Okay? All right. And this is the one the book uses repeatedly. They don't interpolate in the book. If they have a worked out example problem and they have a pump, and it's the ideal Rankine cycle, they're going to use VDP. All right. So now, what about state 7? Well, this were just diagnostic states, state 7 and state 8. And this is just saturated liquid at that pressure. That's just H of F. And then saturated vapor at that pressure, H of G. And then we can have more diagnostics. But let me do this. Let's do this. Which one of these two are 0 for the turbine? Is the turbine have no heat transfer or no work transfer for the first turbine right here? Good. There you go. See? You got one answer right. All day you've been frustrated. There you go. You got one answer right. Now, can you calculate the work of the first turbine? I'm going to pause, walk around. No, yeah, you can do it. You can do it. We're going to leave on here on a high note. All right, I'm going to do an unveiling. I'm going to do an unveiling of this number. So everybody ready to see if you have the right number in front of you? Here goes. 498.5. How did you get it? Yeah, H1 minus H2. All right, so now let's move to the boiler for the reheat. This section right here, what goes into the working fluid in that reheat section. There's no work. And 601.7. How did you get the 601.7? This 601.7 isn't that H3 minus H2? Yeah. All right. Turbine, second turbine. You didn't fool me. 0 on the Q. And then 846. How do you get this 846? H3 minus H4 for the second turbine. All right, condenser. No work done in the condenser. No pressure change in the condenser. It's just heat transfer in the condenser. It comes in with relatively high, exits low enthalpy. So the difference is going to be the H5 minus H4 because you get the negative out. Or it's a negative in, which is an out. So I'm trying to stay consistent with the numbers, positive sign and negative sign in the textbook. Pump we already worked on. And these boilers, those are just diagnostics. To move from 6 all the way to 1, it would be H1 minus H6. So we do it from 6 to 7, H7 minus H6, then H8 minus H7, and then H1 minus H8 for all those 3. And then we do a little diagnostic. We say, of all the heat that comes in to the boiler, okay, 17% of it is going into the working fluid in the reheat. Almost 20%. That's a lot. That's pretty good. And then to heat up the water, well, we're down to 29. Next time we're going to talk about making that much lower. To phase change 40 to superheat 14, counted for 100%. I double checked that my sum of my Q's and the sum of the works balance. I calculate my back work ratio. Excellent. 0.6%, less than 1%. Great. And the thermal efficiency nudges up just a little bit more. Now it's 37%. Well, with that, I'm done for today. I'm open for questions if you have any, and we'll see you next time.